see. So that's great. So we have two, oscillators. And now we want to think about, and we could come up with more. Basically, lots of physical systems do this. It's not just springs and pendula. Other things do it. But now we want to think about what eventually goes wrong. Right? So I'm going to put this here, where this runs into this. Right? Wait a minute, hold on. We want to see, basically, does this go all day? And the answer is, of course, it doesn't. Right? We put it right here. This could be me. And we let it go. And we say, is it ever really going to hit me? Let's see. And you can see on the first one, it doesn't get very close, right? Oh. It's already missing it by quite a bit. Now let's see. This one is already missing it by that much. It's already that far down. So clearly what's happening is it's not doing this. Right? There's no reason the amplitude would decay here. That should go on forever. So already there's something wrong with our equations. So we must fix them. Right? We can't have them broken. Let's see. So what we have to think about how resistive forces affect oscillators. Right. Resistive forces. The most general definition is they oppose motion. And you may think, I'm in good shape because I already know a lot about resistive forces because we've done kinetic friction, right? Kinetic friction. And what was kinetic friction? It was constant, basically. It just depends on the normal force. So that was an easy one. Oh, unfortunately, that's not the one we use here. Sorry. Another one is air drag. All right? That goes as v squared. This little symbol means goes as. It's not an alpha. It's the goes as symbol. There you go. So kinetic friction constant. Air drag goes as v squared. That's exciting, but we can't solve that equation. So that's too hard. Okay? This one is too easy. This one is too hard. Let's do the one that's just right. Liquid drag goes as v. Right? And this is the one that sort of the equations work out, and it's sort of the universal one. Like I said, we like this because this happens in many other systems. It's a very general phenomenon. Lots of systems oscillate. Lots of systems lose energy, and they do it in a way that kind of as though there's a force going as v. So that's the one we're going to use. I got to put this down. Look, it's not even close now. Look at this. Look how much energy we've lost. We've lost that much energy. Look at that. Okay, so the way we do it then is we use the drag force. So by this drag force, we mean in liquid usually. It's usually with some surface that's forced to move up and down in a little liquid column. It's called a dash pot. So the drag force we'll call big D minus BV. So it is proportional to velocity, like I promised. B is the constant, the damping constant between the force and the velocity. Right. It's in kilogram per second. It has no special name. You can see what's in kilogram per second. This is kilogram meters per second squared. This is meters per second. So the only thing left is the kilogram per second. In kilogram per second. So if we were going to draw it here, let's draw the pendulum here in this position and in this position. All right. Then let's draw all the vectors on it. We'd say, well, I got mg down. I'm good at that one. I got tension that way. Right? I've got velocity. At this point, it's always tangential. Therefore, my drag force is just opposite of velocity. Right? It opposes motion. Minus b constant times v. So there's the drag vector, like that. And when it swings the other way, if we assume it's gone up and come back down, then mg, tension, velocity, drag vector, opposing the velocity. Right? And if we wanted to do some IQ test, tricky question, we could say, here's a pendulum. Which way is the drag force? Can you tell me which way the drag force is? No, right? Not enough information. That's a not enough information question because a pendulum can be there and it can be moving this way or that way. Right? The drag force doesn't always pull it down. The drag force always opposes motion. So you have to know which way velocity is to know which way the drag force is. Drag force could be 0. If this is the turning point where it stops moving, then there is no drag force. Right? It's only due to motion in a fluid. Okay? So now, we're going to add that drag force that is slowing down the clock to Newton's second law. Right. Now, we're not really going to be doing these things anymore, right? So we saw the first time we did Newton's second law for the mass and the spring in great detail, got the equation of motion, we guessed an answer, blah, 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 blah. For this one, Newton's second law, we got the equation, we didn't guess an answer, we just gave you the answer, right? Okay, now let's just write the equation. We're not even going to bother, right? So now if I were to add the drag force to Newton's second law, we get something that looks like this for the mass and the spring. Or for any oscillator. This is in terms of a mass and a spring. d2x dt2, that acceleration part, that's the that's the ma part. You get b over m times the velocity. Right? And then you would get k over m times the position. So this is close to how we wrote it before. I think we had this on this side negative. So this is the ma, this is the kx part, but now this is the new drag part. Okay? It's not negative just because we've moved things from one side to the other. But this is sort of the general equation that you get.